write allocate. Okay. So now there are two type of misses. There are two type of misses. One is a read miss and one is a write miss. Okay. Now when you have a read miss, when you have a read miss in a cache, and now we are assuming that we have a private cache. We have a private cache. When there is a read miss, you bring the data,
shared cache.
Bring the data and store it in private cache. Okay?
Yes, sir.
It can be from the shared cache or it can be from the
Main memory.
Okay. Now we have a write miss. Okay, now because it's a write miss. Now let's assume you have some shared resource. This shared resource can be a shared cache or shared main memory. You have some shared resource. I can't say this is shared. Let's assume this is shared cache. Now this is private cache of core 0 and this is private cache core 0 and private cache core 1 and
Excuse me, sir?
1. Now we are only interested. Now this core generated a read miss. Let's assume this data is now 65 and read miss. So now this data will be 65. No problem. Agreed?
Yes, sir.
Now let's assume we have a write miss.
राइट मिस कैसे हो सकता है सर? राइट मिस का क्या मतलब है?
You want to write some data and that data does not exist in the cache. Why not? I will explain this with an example. No problem. No problem. Now listen, this is memory.
ठीक है सर.
Now you have some variable C. Now you want to, and then you have variable A. Now you have variable B. You want to perform this operation. AC is equal to A plus B.
B. ठीक है सर.
This is a read operation or write operation?
Read operation.
This is a read operation or write operation?
Read operation.
This one is a
Write operation.
write operation. This C that is reside in memory. You want to read
ठीक
C.
है सर.
You want to write C.
ठीक
Or
है.
C does not exist in cache.
ठीक है सर.
समझ आई बात?
Yes sir.
Okay. Any question? Any confusion?
Clear,
No.
sir.
Okay. Now you want to read this data in 65 your data, and then let's assume the tag is tag of A. Tag of A. So this is stored in the PC with the tag A. This is read miss. Tag of
A.
A.
Read miss.
Now write miss. I want to have tag of C.
C.
Tag of C. So it means now you want to write the data is not there. So first you want to write some data, you want to write some data. So let's assume this value in tag of C, initial value is 37 and there is a write miss. So first you update in shared resource and then bring it. Okay, so now the new value, so let's assume if its new value is 95, its new value is
95.
95. So what it will update? 95 and bring this 95 to tag of C and its new value is now 95. So in the write miss, you first update it in the shared resource and then bring it in the cache because it's a write miss.
ठीक है सर.
समझ आई बात?
राइट मिस के केस में फिर कैश में लाने की जरूरत क्या है सर?
So what's the policy? What's the name of the policy? Write through, write,
ठीक है.
allocate. In write through, write, allocate, first we update the main memory and then bring it into the cache. And now we have another policy, write through with no write allocate. So this is one is same. When there is a read miss, bring the data and put it in the cache, no problem. When there is a write miss, you update it in the shared resource, but you do not bring it in the cache. So number 2, write miss, update in main memory
ठीक है
But do not update, do not
अपडेट इन द प्राइवेट केस
bring it to cache
प्राइवेट केस सर
into private cache.
प्राइवेट केस
Okay? Okay. So write is updated into main memory. Main memory or it is a shared, it can be a shared cache.
ठीक है सर
Okay.
सर राइट थ्रू में क्या होता था जब राइट थ्रू में जब राइट मिस होता था तो उसमें क्या होता था सर
Write through, देखिए, write through has two variations.
टू
Write
वेरिएशन
through with write allocate and write through with no write allocate.
ठीक है सर
In write through with write allocate, when there is a write miss, you update the data in the shared resource and then bring it into the cache.
ठीक है सर
Okay? But in write through with no write allocate, you update it in the shared resource but do not update it in the private cache. So in this case, this 95 will not be brought and it will be updated only
एंड शेयर्ड
here.
रिसोर्स
Why? This is an advantage because when it's a write intensive data,
ठीक है सर
जब आप डेटा को अपडेट कर रहे हो तो इसकी प्रोबेबिलिटी ज्यादा होगी, वो अगेन राइट होगा.
ठीक है सर
ठीक है? सो देन यू विल हैव डबल राइट. अगली दफा जब वो राइट होगा, so you will also update it here and updated it here. But next time it will be only updated here.
ठीक है सर
समझ आई बात? अगर नेक्स्ट टाइम पे वो रीड होगा तो रीड मिस होगा, फिर वो दोबारा यू विल ब्रिंग इट इनटू द कैश. नाउ लेट्स you write c is equal to a plus b. It's a right hit or a right miss?
राइट मिस
Right miss. Now after some time you have e is equal to c plus b. Then
इट विल बी रीड हिट
it be,
अगर उसने एलोकेट किया केशे
अगर allocate किया है तो it will be a read hit.
हिट ठीक
अगर
है सर
allocate नहीं किया, there is a read miss.
ठीक है सर
समझ आई बात नहीं आई? So actually this
तो ये
is
पॉलिसी कौन सी यूज होगी सर मतलब
depending upon the architecture. अब आपके पास गाड़ी है, एक में मैनुअल गियर है, एक में ऑटोमेटिक है. अब कहेंगे कि आप एक गाड़ी में दोनों गियर सिस्टम तो यूज नहीं हो सकते ना.
ऑटोमेटिक ठीक है ना सर
Only one will be used. Either right through with right allocate will be used or right through with no right allocate will be used. Now it depends on the pattern of the data. If there are a large number of right misses, which policy is better?
अगर मिसेस है सर
Right misses,
राइट मिस है तो
no right allocate. अब देखिए कितने बड़े.
दो जगह पे उन्हें अपडेट
यही तो क्वेश्चन है ना. I will ask these simple kind of questions in the logical reasoning. So I will say assume a scenario that we are using a right through with no right allocate policy and there are a large number of right misses. Which policy is better? Right through with right allocate or right through with no right allocate? अब ये जो लॉजिकल रीजनिंग के क्वेश्चंस होंगे, इस तरह के क्वेश्चंस आपके यू विल एक्सपेक्ट देम इन द एग्जाम्स एंड देन एक्सप्लेन विद रीजन. ठीक है? Which policy is better? Right through with no right allocate, right through with no right allocate. Which policy is better? Now let's assume a scenario. You have 48 cores and you want to maintain the consistency and you have a coherence directory. What is the overhead of this coherence directory? You have 4 cores. Which policy is better? Policy 1, policy 2, policy 3 or policy 4? Now if you have 4 cores and you want to maintain a coherence directory, it's simple, no problem. But if you have 48 cores, maintaining coherence directory is difficult. How you can avoid this problem? You cluster them.
यस सर
You cluster them. You divide it into different regions, and you maintain coherence among regions. Now ये भी तो हो सकते हैं ना कि ये जो होगा इसके लिए separate address space होगा.
यस सर
It will not access address space of this, and it will not access space of. So maintaining coherence among the regions is not necessary, but maintaining coherence within the region is necessary.
सर इस केस में अगर हम इस तरह से क्लस्टर्स बनाएंगे तो इनके नीचे एक और शेयर्ड मैप होगी.
नहीं, उसमें से ये होगा कि अब ये मेमोरी मैप है.
ये डायरेक्ट मेमोरी से होंगे.
ये मेमोरी मैप है ना. तो अब देखते हैं जो एड्रेस स्पेस है कोर 0 से कोर 3 के लिए, these cores will not access this address space.
लेकिन ये जो शेयर्ड स्पेस है ये शेयर्ड स्पेस है, इसके नीचे एक और शेयर्ड स्पेस भी
नहीं, उसमें से ये होगा कि ये प्राइवेट एंड शेयर्ड, प्राइवेट एंड शेयर्ड. अब देखिए अब जितने नंबर ऑफ कोर्स है, अगर आप शेयरिंग तमाम के दरमियान शेयरिंग करना चाहेंगे तो एक प्रॉब्लम हो जाएगी ना. ये कि कुर्सी एक है, आपने चार लोगों के दरमियान शेयर करनी है. लेट्स अज्यूम यू वांट टू हैव अ म्यूजिकल चेयर. 4 के दरमियान तो ट्रैक्टेबल है नहीं, लेकिन अगर ये चेयर्स आप शेयर कर रहे हैं 48 लोगों के दरमियान तो यहाँ पे तो प्रॉब्लम ही हो जाएगी ना। तो आपने तो चीज़ों को देखना भी है कि आपने मैनेज कैसे करना है ना। बीइंग एज ए कंप्यूटर आर्किटेक्ट, being a computer architect, you need to see that which policy is more tractable or which policy is more intractable, which policy is suitable in which particular scenario. Now, if our requirement is if we want to increase the number of cores, what can be the suitable policy? सही समझ आ रही बात ये?
Yes, sir.
ये चीज़ है. And why multiple cores are important? Now, if you look at our applications, especially in a server-based system, when multiple applications are running on a server, so actually you need multiple independent cores. You need multiple cores. If you have many cores, your degree of parallelism is better. But it also depends upon the degree of the sharing resources. So now if you have multiple cores and you are running multiple independent applications or different core independent applications that are not sharing any data, the problem becomes simple. But if you are sharing some data among many applications, then the problem will become more complex. The problem will become more and more complex. And why the problem will become more complex? I will explain this with an example. Now let's assume we take an example. Okay. Now if you look at a banking system, now in a banking you have an account, and in your account you have some money. And this account is connected to all of these ATMs. Now you go to ATM number 1 and access this data. And some other guy has also your same ATM information and we log into from another data. And it collides. Now you are making two transactions. You are making transaction from an ATM. Now you are making a transaction from your mobile application.
Yes.
Now the problem arises. अगर आप एटीएम चेक करना चाहते हैं तो बेसिकली जब वो होगा तो वो पहले अकाउंट को लॉक करेगा,
कोई और सोर्स से ट्रांजैक्शन ना हो।
वो अगर इधर से ट्रांजैक्शन कर रहा हो, आपके अकाउंट में 25,000 पड़े हुए हैं, आप इधर से भी 25,000 की ट्रांजैक्शन कर रहे हैं, उधर से भी ट्रांजैक्शन कर रहे हैं। आप देखिए ये कम्युनिकेशन हो रही है या नहीं हो रही? ठीक है, तो बेसिकली जब बैंक वाले हैं तो इन सिनारियो को एंटिसिपेट तो उन्होंने करना है ना। तो बेसिकली जब डाटा इज शेयर्ड अमंग, अब देखो जब वो डाटा वो करते हैं तो वो डेटाबेस एप्लीकेशन होगी, वो क्वेरी डालेगा, जब वो क्वेरी डालेगा तो फिर वो उसको लॉक करेगा, जब लॉक करेगा तो यू कैन नॉट एक्सेस इट फ्रॉम अनदर ट्रांजैक्शन। जाहिर बात है कि अब बैंकिंग वाले ये सोचेंगे नहीं।
yes.
ठीक है, तो इसी तरह से व्हेन यू वांट टू डिजाइन अ सिस्टम, ठीक है, और यू आर रनिंग मल्टीपल एप्लीकेशंस ऑन मल्टीपल कोर्स, सो यू नीड टू थिंक ऑफ दीस कंसिस्टेंसी प्रॉब्लम्स। Okay, so now you have write through with write allocate, write through with no relation. Agreed?
Yes, sir.
Okay. Now what is read through, load through? Read through, load through. Read through, load through is a concept that applies to any kind of cache. It can be a write through cache, it can be a write back cache. Read through, load through. So if you want to access the data from main memory, typically the size of the bus between the main memory and the microprocessor based system is limited. So now let's assume we have this main memory. Now you have a cache here. It can be cache and it can be a microprocessor or private cache. Okay. So typically the granularity of the cache line, what is the typical granularity of a cache line? I told you in the last lecture. What is the typical granularity of a cache line? The size of the data. मैंने आपसे ये कहा था कि the granularity from the main memory to the hard disk is typically in terms of pages, and the page size is typically 4 kilobyte or 8 kilobyte, if you remember.
Yes, sir.
What is the granularity of the transfer between the main memory and cache? The cache line size. What is the typical cache line size?
64
byte.
Right.
So a typical cache line is 64 bytes. Okay. Now, if you look at the 64 byte, okay, so we can divide it into different words. We can divide it into words 0, word 1, word 2, up to word
words
15. word 0, word 1, word 2, word 3, up to word 15. Okay, now the cache line size is 64 byte. What is the word size?
4 bit,
4 byte.
4 byte.
And the size of the bus, let's assume the size of the bus is equal to the word size. So the size of the bus is 4 bytes. 4 bytes are 32 bits. What is the cache line size? 512 bits. But the size of the bus between the cache and the main memory is
30.
limited. Now let's assume if you want to access word 0, you can access it directly. But if you want to access word 10, if you want to access word 10, so what microprocessor want to access word 10? So microprocessor wants to say, read word 10 of main memory block J. So this is main memory block J. Now if you bring word 0 first, then word 1 up to then word 10, so the latency will be higher or lower? Higher. What is the best policy? First load word 10 and then bring word 0, word 1 up to. This is called as read through, load through. We also call it as a critical word first. Critical word first. So the critical word first in this case, first word 10 is transferred.
सर word 10 कैसे critical word हो गया, समझ नहीं आई.
अच्छा, okay. Let's assume I say load. Microprocessor has this data. Load word 10 of main memory block J. अच्छा, assembly instruction से क्या होगी? Load R3
Yes sir.
in some register R3.
Yes,
ठीक है? Address of W10.
Yes sir.
फिर आप ये कहेंगे कि add R3, R4, R3, R5. अच्छा, अब देखिए ये इंस्ट्रक्शन उस वक्त एग्जीक्यूट होगी जब you will get the value of R3.
Yes sir.
R3 कहाँ पड़ा हुआ है? word 10 में.
word 10 में पड़ा हुआ है.
अच्छा, अगर हम इस तरह से कर दें पहले word 0 ट्रांसफर करेंगे, इसमें 4 साइकिल लगे, फिर word 1 4 साइकिल and up to word 10 4 cycle. How many cycles will you require to get word 10?
ठीक है sir.
40 cycles.
Yes sir.
So what I say, instead of bringing word 0 first, you fetch word 10, provided it to the microprocessor gets the data first, word 10, and then you bring word 0, word 1, word 2.
40 साइकिल में 10 साइकिल नहीं रखते सर, एक साइकिल में एक वर्ड आ गया, दूसरे में दूसरा.
किसमें?
एक साइकिल में एक वर्ड नहीं
Now
आता.
let's assume the memory latency is higher.
ठीक है सर.
Memory operated at smaller frequency and microprocessor operated at a higher frequency. Let's assume its frequency is 800 megahertz and its frequency is 33.2 gigahertz. So the microprocessor frequency is higher.
ठीक है सर.
Memory frequency is lower. To get word it requires 4 cycles.
ठीक है सर.
It requires 4 cycles. ठीक है? अगर आप word 10 की बात करेंगे तो it will be fetched very later. So in the read through, load through, when you want to access, microprocessor want to access some words, so it will first fetch the critical word and then bring the whole block and put it in the cache. क्योंकि माइक्रोप्रोसेसर को अब नाउ क्या चाहिए, कौन सा वर्ड चाहिए?
Word 10 चाहिए.
Word 10 चाहिए. जब वो word 10 चाहिए तो basically it will bring word 10 first and then word 0, then word 1 and then word 15. And if later on microprocessor wants word 1, then it will be a hit in the
It will be a hit.
hit in the cache and then it will access. Which locality is this? Spatial or temporal? Spatial or temporal? Spatial. If you access word 10 now and then later on you access word 0. It's spatial locality because they are adjacent in space, not adjacent in time. And you, if you access the same item,
Again and again to be temporal loop.
it's a temporal locality. So loop counter, loop variable. Loop variable is example of temporal locality or spatial?
Temporal.
Temporal locality. And arrays are example of
Spatial.
spatial locality. Okay?
Yes, sir.
So this concept is called as read through,
Load
load through. It's also called as critical word first. Critical
word first.
word first. Okay, now we have different type of misses, cache misses. We study different type of cache. कौन से cache हमने study किए हैं? Direct map cache,
Associative.
associative cache and
Set associative.
fully associative cache.
Yes, sir.
Okay. So now we have three type of messes. We have first compulsory mess. We have three type of cache messes, which is known as direct map, set associative, and
Fully associative.
set associative, and then
Direct map.
direct map cache. Compulsory mesh. What is a compulsory mesh?
केशे में हो ही ना.
क्या कहें?
When the data is first time brought from
Yes, when the data is first brought from the main memory and it's not there, we also call it compulsory mesh or cold mesh. When your system is initially started, all the data is in the hard disk. Then the data is brought from the hard disk to your main memory. Okay? And when microprocessor access that data, then it will be brought from the main memory to the cache for the first time. For the first time. This type of mesh is called as compulsory mesh. Independent of the cache,
ये
so
हर
the
एक में
compulsory
होगा.
mesh exists in all type of cache. Now there is a conflict mesh.
ये सिर्फ डायरेक्ट मैप में होगा.
It also exists in direct map, but it also exists in
लेकिन
set
उसमें
associative.
बहुत कम होगा.
No, set associative exists. It exists. I will explain this with an example. I will explain this with an example. Now let's assume you have a main memory. And now you have some cache. And it is actually direct map cache. It is a
Direct
map cache. Let's assume we have only 4 sets. Set 0, set 1, set 2 and set 3. So main memory block 0 will be mapped here. Then which block? 4, 8, 12 and so forth so on.
Yes.
Okay. Now let's assume microprocessor want to access MB0, main memory block 0. Okay. To which set it will
Set
be mapped?
0.
Set 0. So main memory block 0 will be mapped. Now microprocessor want to access main memory block 1, main memory block 2, main memory block 6, main memory block 10. Microprocessor want to access main memory block 6. To which set it will be accommodated?
6
Set
के
2.
लिए is it 2?
Okay, these two slots are now empty.
Yes, sir.
These two slots are now empty. Microprocessor want to access memory block 8. Block 8. Which block will be replaced?
MB0,
MB0. What will be the new block?
MB8,
MB8. Now this type of mesh is called as
conflict mesh.
mesh. Even the space in set 1 is available. Even the space in set 1 is available, but this mesh occur because of a conflict. This mesh occur because of a conflict. So this conflict mesh occur in a direct map cache. Yes.
ठीक है सर.
Okay. Now we have another example. Now we have two-way associative cache. We have two-way associative cache. These are two-way associative cache. Okay. Which block will be mapped here? MB0, MB1, MB4, MB8, MB12, MB what? MB1, MB5,
9.
MB9 and so forth so on. Okay. Now this is you. MB3, MB7, MB11 and so forth so on. Let's assume this is in access to memory block 0. Where it will be accommodated? Here. Again MB8.
ठीक है सर.
Okay. Again
MB4.
MB3.
Yes sir.
Now MB12. MB12. So actually it will replace either MB0 or MB8 depending on the replacement policy. Let's assume this MB0 is replaced. This MB0. What is the new value?
M12.
MB12. Still this cache has empty places,
Yes sir.
but it also exists in
Associate.
a set associative
Set
cache.
associative.
Yes.
ठीक है सर.
But in fully associative cache, conflict miss will never arise. Because in fully associative cache, instead of you have 4 sets, in fully associative cache you have only a
One set.
single set, that is
Set 0.
set 0. And all of the blocks will be mapped here. All the blocks will be mapped here. Now if you have MB0, you put it here. Now you put MB8 here, then MB3 here, then MB12
Yes sir.
MB12 here. But now in fully associative cache you have a single set. When you have single set, and all memory blocks from the main memory are
Can map in the
can be mapped here. So there will be no chance of conflict miss. So the conflict miss does not occur in
fully associated.
and fully associative cache. Now receiving the total number of cache lines that can be mapped here or total number of cache lines of L. So when there will be replacement in set 0, a single set, when it becomes
Full.
full. When it becomes full, it means it is now, its capacity is now O1. When its capacity is 1, so this type of miss is called as
Capacity miss.
capacity miss. So the capacity miss occur in fully associated case, but it does not occur in direct map cache. In direct map cache, the type of conflict is now conflict is not capacity miss. देखिए डायरेक्ट मैप कैश में ये होगा कि कुछ एमडी कैपेसिटी की वजह से वो नहीं हो रहा है,
Conflict की वजह
conflict की वजह से होगा. और जो फुल एसोसिएटेड जो रिप्लेसमेंट होगी, that replacement is because of what?
Capacity conflict की वजह से नहीं है.
Capacity conflict की वजह से नहीं है. So these are two contradictory terms. So when there is a conflict means there will be no capacity miss, when there is capacity there will be no conflict miss.
ठीक है सर.
ठीक है? So okay. So this and conflict miss arises when multiple blocks are mapped to the same set. And this replacement is done because of the conflict. Even some other sets have empty locations.
Empty locations.
Even if other sets have some
Empty locations.
empty location, but still because the memory blocks that are mapped to that sets are mapped to the same set, and it's because of the conflict. Now I will explain this with an example. Now let's assume if these are two chairs here, one chair here, and one chair here. Okay, and I say all the students who are sitting in this region can only sit on this chair, and all the students who are sitting in this region can only sit on this chair. But if this student wants to come here, now she sits here. Now if she wants to sit here, now we have to kick her out and bring in
Yes sir.
the new one. Even that chair is empty.
Empty. A conflict
It's
was.
because of the conflict, because this chair is being shared by all the students who are sitting in this region.
ठीक
They
है.
cannot sit in this region. Okay? So this type of miss is called as
Conflict miss.
And now in a fully associated cache, now if we have now these two chairs, and any students from any region region can sit on here.
Yes, sir.
So in this case, so actually now if she wants to sit, she will sit here, and she wants to sit, she will sit here. Now if
Capacity.
third person comes here, now it means all the capacity is full now.
Yes, sir.
So now we are negative. Now one out.
ठीक.
So it's not because of the conflict, it's
Due to
because of
capacity.
the capacity. It's because of the capacity. So the capacity means occurs only in fully associative cache, and conflict means occur in direct map cache and set associative cache. And it's because of the mapping policy. Because in a mapping policy, certain blocks are mapped to a particular set. They cannot go to another set. But in fully associative cache, any block can get to that a single set because set is single. Okay. So close करते हैं. Now we